When I talk about the fate of spacetime, I have to start with entropy. Entropy is not a vague idea about disorder. It is a precise concept in physics. It measures how many microscopic configurations correspond to what we see on large scales. The more ways a system can be arranged internally while looking the same from the outside, the higher its entropy. A gas spread evenly in a box has high entropy because the molecules can be arranged in many ways and still look uniform. A gas squeezed into one corner has low entropy because there are fewer possible internal arrangements. The second law of thermodynamics says that for an isolated system, entropy tends to increase. It does not say it never goes down, but it says that overwhelmingly, the most likely direction of change is toward higher entropy. Our universe, as far as we can tell, behaves like an isolated system on large scales. So when we ask about the fate of spacetime, we are really asking how entropy will shape the long-term evolution of the cosmos under the influence of gravity, dark matter, and dark energy. To understand why this is so powerful, I need to connect entropy to spacetime itself. In everyday physics, we think of entropy in terms of heat flowing from hot to cold, or ice melting, or batteries running down. But in cosmology, gravity changes the story. Gravity is attractive. It pulls matter together. That seems like it should create order, not disorder. A diffuse gas cloud collapsing into a star looks like a move from messy to organized. Yet in thermodynamic terms, gravitational clumping actually increases entropy. There are many more ways for matter and radiation to be arranged in a universe that has stars, galaxies, and black holes than in a universe that is perfectly smooth. The key is that gravitational systems can radiate energy away, for example, as light or gravitational waves, and then settle into more tightly bound states. That process opens up more microscopic possibilities. So, in a universe with gravity, high entropy often looks like structure, and the ultimate high entropy objects are black holes. Black holes are crucial because they tell us something deep about the link between entropy and spacetime geometry. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes have entropy and that this entropy is proportional to the area of the event horizon, not the volume inside. Hawking also showed that black holes radiate like black bodies with a certain temperature. This is Hawking radiation. Together, these ideas gave us the Bekenstein-Hawking entropy formula. It says that the entropy of a black hole is enormous compared to ordinary matter of the same mass. In simple terms, a black hole is the most entropic way to store a given amount of mass and energy. This means that as the universe evolves, matter tends to fall into black holes because that is one way for entropy to increase. The geometry of spacetime around a black hole encodes this thermodynamic behavior. That is one of the first hints that entropy is not just about particles. It is also about the structure of spacetime itself. Now let me zoom out to the whole universe. Observations of the cosmic microwave background, galaxy surveys, and supernovae tell us that the universe is expanding and that this expansion is accelerating. The main evidence for acceleration comes from type 1a supernovae, which act as standardizable candles. In the late 1990s, 2 independent teams measured distant supernovae and found they were dimmer than expected in a decelerating universe. The simplest explanation was that the expansion rate has been speeding up for the last few billion years. When we combine this with measurements of the cosmic microwave background from missions like WMAP and Planck, and with galaxy clustering data, we arrive at the standard cosmological model, often called LCDM. In this model, about 5% of the universe is ordinary matter, about 25–27% is dark matter, and about 68 to 70% is dark energy, which we usually model as a cosmological constant, LEL. Dark matter is dark because it does not emit, absorb, or scatter light in any significant way. We infer its presence from its gravitational effects. Galaxy rotation curves stay flat at large radii, rather than falling off as they would if only visible matter were present. Gravitational lensing shows more mass-bending light than we can account for with stars and gas. The cosmic microwave background power spectrum also demands a non-baryonic matter component to match the observed pattern of temperature fluctuations. Dark matter clumps under gravity and forms the scaffolding on which galaxies and clusters grow. It contributes to the large-scale structure of the universe, the cosmic web of filaments and voids we see in surveys. Dark energy, in contrast, does not clump on small scales as far as we can tell. It acts like a smooth component with negative pressure. In general relativity, not only energy density but also pressure gravitates. A component with sufficiently negative pressure can drive accelerated expansion. A cosmological constant is the simplest form of dark energy. It is a constant energy density filling space with an equation of state parameter W equals PR equal to -1, where P is pressure and VOR is energy density. This value leads to a repulsive gravitational effect on large scales. Observations so far are consistent with W being very close to -1. There is still room for small deviations, but no strong evidence for them yet. So we have a universe whose expansion is dominated by dark energy and whose structure is shaped by dark matter and ordinary matter under gravity. How does entropy evolve in such a universe, and what does that tell us about the fate of spacetime? To answer that, I need to think about the timeline of the universe in broad strokes. Right after the Big Bang, the universe was hot, dense, and nearly uniform, with tiny fluctuations. That early state actually had very low gravitational entropy, even though the thermal entropy of radiation was high. The low gravitational entropy came from the smoothness. There were very few gravitational clumps. Over time, those tiny fluctuations grew under gravity into galaxies, clusters, and superclusters. Entropy increased as matter collapsed, stars formed, nuclear fusion ran, and black holes grew. We see evidence for this history in the cosmic microwave background. The CMB is the afterglow of the hot early universe, released about 380,000 years after the Big Bang, when electrons and protons combined to form neutral hydrogen and the universe became transparent to radiation. The microwave background is extremely uniform, but it has temperature fluctuations at the level of 1 part in 100,000. Those fluctuations are the seeds of structure. Their statistical properties, measured in detail by Planck and other experiments, match the predictions of inflationary cosmology and the CDM model. From these data, we infer the matter content, the geometry, and the age of the universe. We also infer that the early universe was remarkably smooth, with low gravitational entropy. As time goes on, stars burn their nuclear fuel and die. Massive stars explode as supernovae and leave behind neutron stars or black holes. Smaller stars shed their outer layers and become white dwarfs. Black holes in galactic centers grow by accreting gas and merging with other black holes. This whole process converts low-entropy fuel like hydrogen into higher entropy products like radiation and heavier elements, and into black holes with huge entropy. The entropy budget of the observable universe today is dominated by supermassive black holes in galactic centers. Their entropy is vastly larger than the entropy of all the ordinary matter and radiation combined. Now add dark energy to this picture. In a universe with a positive cosmological constant, the expansion accelerates and there is a characteristic horizon scale called the de Sitter horizon. Beyond this horizon, regions of space recede from us faster than light due to the expansion of space itself, and light emitted from there now will never reach us. This is not a violation of special relativity. It is a feature of general relativity and expanding spacetime. The de Sitter horizon is similar to a black hole horizon in one important way. It has an associated temperature and entropy. A universe dominated by a cosmological constant behaves like de Sitter space, And de Sitter space has a maximum entropy proportional to the area of its horizon. So if dark energy really is a cosmological constant, then our universe has an ultimate entropy bound set by this de Sitter horizon. This leads to a picture often called the heat death, or thermal equilibrium of the universe, but in a gravity plus dark energy context. In the far future, if dark energy remains constant, the expansion will continue to accelerate. Galaxies that are not gravitationally bound to us will eventually cross our cosmological horizon and become causally disconnected. Over tens of billions of years, star formation will slow as gas is used up or locked away in remnants. The universe will become a collection of isolated gravitationally bound systems, like galaxy groups and clusters, each surrounded by an expanding, increasingly empty space. Within each bound region, black holes will dominate the entropy. On even longer timescales, black holes themselves will slowly evaporate via Hawking radiation. The timescale for a stellar mass black hole to evaporate is around 10 to 67 years. For a supermassive black hole with 1 billion solar masses, the evaporation time is around 10.99 years. These numbers are unimaginably large compared to the current age of the universe, which is about 1.38 times 10 years. But if we follow the laws of physics as we understand them, and if the cosmological constant stays constant, then eventually black holes will radiate away their mass and disappear, leaving behind a bath of very low-energy photons and other particles in an ever-expanding spacetime approaching de Sitter space. Entropy will be near its maximum allowed by the horizon area. There will be no significant free energy gradients left to drive complex processes. That is what we mean by the thermodynamic fate of spacetime in an ill-dominated universe. However, this picture depends on several assumptions that we cannot yet fully test. One assumption is that dark energy is exactly a cosmological constant with W equals -1, and that it remains constant forever. Observationally, we measure W by looking at the expansion history using supernova, baryon acoustic oscillations, the cosmic microwave background, and other probes. Current data are consistent with W equals -1 within a few percent, but small deviations are still allowed. If W is slightly greater than -1 and maybe varies with time, dark energy could be a dynamical field, often called quintessence. In that case, its energy density might change in the future, possibly decaying away. The universe could then transition from acceleration back to deceleration or to some more complex behavior. Our predictions about the ultimate fate would change accordingly. If W is less than -1, we enter the regime of phantom energy. In simple models, phantom energy leads to a big rip scenario. The energy density of dark energy grows with time, and the expansion accelerates so violently that eventually even bound structures are torn apart. First galaxy clusters, then galaxies, then solar systems, and finally atoms and nuclei. In a big rip, space-time reaches a singular state in finite time. This is a dramatic alternative to heat death, but it depends on dark energy having properties that are challenging to reconcile with quantum field theory and stability. Observationally, values of W significantly below -1 are disfavored, but small excursions cannot be fully ruled out yet. So the big rip is not the favored scenario, but it is a logically possible one given current uncertainties. Another assumption is that the laws of physics we know today continue to apply in the same form over arbitrarily long times. That includes general relativity, quantum field theory, and our understanding of black hole evaporation. Hawking radiation is a robust theoretical result, but we have never observed it directly. Black holes that we can see are far too massive and cold for their Hawking radiation to be detectable against other sources. The thermodynamic description of horizons, including de Sitter horizons, is based on semi-classical gravity, where quantum fields live on a classical curved spacetime. A full theory of quantum gravity might modify some of these conclusions, especially about the ultimate fate of information and the detailed microscopic origin of entropy. There is also the cosmological constant problem. The observed value of dark energy density is extremely small compared to naive theoretical expectations from quantum field theory. If we sum up the zero-point energies of quantum fields up to some high-energy cutoff, we get a vacuum energy density many orders of magnitude larger than what is observed. The fact that the cosmological constant is non-zero but tiny is one of the biggest puzzles in fundamental physics. We do not know why it has the value it does. Some approaches invoke anthropic reasoning in a multiverse where only regions with small L allow galaxies and observers to form. Others look for new symmetry principles or dynamical mechanisms that set L to near zero. None of these ideas is universally accepted or experimentally confirmed. This uncertainty about the nature and origin of dark energy feeds directly into our uncertainty about the long-term fate of space-time. Now let me connect this back to entropy more directly. One of the striking facts about our universe is that it started in a state of very low gravitational entropy. The cosmic microwave background shows a nearly uniform density. That is a special state among all the possible configurations allowed by gravity. Most configurations would be much more clumpy. Why did the universe begin in such a special low-entropy state? We do not have a complete answer. Some ideas suggest that inflation, a period of accelerated expansion in the very early universe, can explain some aspects of the initial conditions. Inflation can take a small, smooth patch of space and stretch it to enormous size, ironing out inhomogeneities. But inflation itself requires initial conditions, and it is not clear that it fully explains the low entropy beginning. This past hypothesis problem, the question of why the early universe had low entropy, remains open. The link between entropy and spacetime also appears in the holographic principle. Inspired by black hole thermodynamics and string theory, the holographic principle suggests that the maximum entropy in a region of space is proportional to the area of its boundary, not its volume. That is a radical departure from ordinary field theory intuition, where the number of degrees of freedom scales with volume. In certain special spacetimes, like anti-de Sitter space, we have a concrete realization of this idea in the ES-CFT correspondence. There, a gravity theory in a bulk spacetime is equivalent to a non-gravitational quantum field theory living on its boundary. For our universe, which appears to be closer to de Sitter than anti-de Sitter, we do not yet have a fully developed holographic dual. But the de Sitter horizon entropy hints that a holographic description might exist. If so, the fate of spacetime might be encoded in a fundamentally different, perhaps lower dimensional description. This is still speculative, but it is grounded in serious theoretical work. When I ask about the fate of spacetime under the influence of dark energy and entropy, I also have to think about the role of dark matter in the long term. Dark matter drives structure formation by providing most of the gravitational mass in halos. In the future, dark matter will continue to sit in these halos, but as star formation winds down, there will be fewer luminous tracers. Dark matter itself seems to be stable on cosmological timescales, at least for the simplest candidates, like weakly interacting massive particles. We have not detected dark matter particles directly yet, despite many experiments using underground detectors, colliders, and astrophysical observations. But the gravitational evidence is strong. If dark matter is truly stable, then in a heat death scenario, it will eventually be either swallowed by black holes or left as a dilute cold component in an expanding de Sitter background after black holes evaporate. If dark matter can decay on extremely long timescales, it might slowly convert into radiation or lighter particles, changing the late-time composition, but not the basic entropy story. We do not yet know which is true. I should also mention that our current cosmological model assumes that general relativity is the correct description of gravity on all scales. We have tested GR very well in the solar system, in binary pulsars, and with gravitational waves from merging black holes and neutron stars. On cosmological scales, GR combined with dark matter and dark energy fits the data well. But some researchers explore modified gravity theories, which try to explain cosmic acceleration without invoking dark energy, or to address other issues. These theories often introduce new fields or change the behavior of gravity on large scales. They are constrained by observations, but not completely ruled out. If gravity is modified in the far future, the fate of spacetime might differ from the standard LCDM picture. Right now, though, LCDM with GR is the simplest model consistent with the data, so it is the baseline for discussing entropy and cosmic destiny. One more subtle point concerns horizons and information. In a de Sitter universe, we have a cosmological horizon with a finite entropy. That suggests a finite number of degrees of freedom in the observable patch. If that is true, then the evolution of the universe might be more like a finite state system, and questions about recurrence and long-term behavior become non-trivial. In classical thermodynamics, a system with finite entropy can, in principle, undergo Poincare recurrences, where it returns arbitrarily close to a previous state after an enormously long time. Whether something like that makes sense in quantum gravity for de Sitter space is not clear. The combination of horizon entropy, quantum mechanics, and cosmic expansion leads to deep questions about what it even means to talk about the ultimate fate of spacetime. We do not have a complete, agreed-upon framework for this yet. So, putting everything together, here's the current mainstream picture, with its caveats. The universe began in a hot, dense, low gravitational entropy state. It expanded and cooled. Tiny fluctuations grew under gravity into the large-scale structure we see. Dark matter provided most of the mass for this growth. Ordinary matter formed stars and galaxies. Nuclear fusion and gravitational collapse increased entropy, especially by forming black holes. At some point, a few billion years ago, dark energy began to dominate the expansion, causing acceleration. If dark energy is a true cosmological constant and remains so, the expansion will continue to accelerate. Structures that are not gravitationally bound will drift beyond our horizon. Star formation will end. Black holes will dominate the entropy and then slowly evaporate. Eventually, the universe will approach an empty, cold, de Sitter-like state with a finite horizon entropy and no significant free energy gradients. That is a kind of thermodynamic end state for spacetime. But this picture rests on open questions. We do not know what dark energy is at a fundamental level, or why its density has the value we observe. We do not know the full theory of quantum gravity, so we do not fully understand the microscopic origin of horizon entropy or the ultimate fate of information. We do not know why the early universe had such low gravitational entropy. We do not know the exact nature of dark matter, or whether it is perfectly stable. We do not know whether the equation of state of dark energy is exactly -1 or only approximately so. Each of these unknowns could, in principle, alter our conclusions about the long-term fate of spacetime. So I end with one specific open question that's at the heart of this topic. Is the dark energy that drives our current cosmic acceleration truly a constant property of spacetime with a fixed equation of state W equals -1? Or is it a dynamical field that will evolve in the future and change the ultimate thermodynamic fate of the universe?